Welcome to the deep dive. Today, we're plunging into something really significant, a technological marvel, maybe, that could fundamentally reshape how we trust and interact with artificial intelligence. We're talking about VaultGemma. Now, that name might not be on everyone's radar just yet, but believe me, its implications are, well, they're massive for the future of secure AI. Okay, imagine this scenario. You've got this advanced AI, right? And it's analyzing super sensitive data, maybe confidential medical records or, I don't know, proprietary financial documents. And then it inadvertently memorizes a specific detail, just, picks it up from the training data. And later, maybe completely out of context, it just reveals that private snippet, word for word.
Yeah, and that's not just like a theoretical worry.
Right, it's real.
It's a documented vulnerability in a lot of large language models out there today.
Yeah.
And it's a huge barrier, a real roadblock for AI adoption in critical sectors where privacy isn't just nice to have, it's essential.
Exactly. And VaultGemma is Google's, well, monumental answer to that very problem. So our mission for this deep dive, we want to unpack not just what VaultGemma is, but why it exists. How does it actually work under the hood? And crucially, what does its release mean for all of us? As we try to build AI systems that are genuinely safe, transparent, and ultimately trustworthy. What makes this model such a game changer?
Well, it's really not an exaggeration to call VaultGemma a true milestone. I mean, for years, the AI community has been wrestling with this exact challenge. How do you build these incredibly powerful language models without that lingering risk of them accidentally exposing sensitive training data? VaultGemma steps right into that gap. It's the largest open-weight, 1 billion parameter large language model, or LLM, that's ever been trained entirely from scratch with the really rigorous mathematical guarantees of differential privacy, DP, as it's often called. Its arrival, its release. It directly addresses one of the most critical bottlenecks that's been holding back broader AI adoption, especially in those sensitive areas, healthcare, finance, where confidentiality is, a legal and ethical mandate. And what's truly revolutionary, I think, is its privacy by design philosophy.
Privacy by design, okay.
Yeah, this isn't some kind of security patch you add later, or an afterthought bolted onto an existing model. Differential privacy is woven right into the very fabric of its pre-training process from day one. And the result? It's pretty extraordinary. Empirical tests have shown literally zero detectable memorization of its training data.
Zero. That's a big claim.
It is. Now, we should be upfront, totally transparent. This groundbreaking privacy, it does come with a cost. We often call it a privacy tax.
Ah, the privacy tax.
Right. It's raw performance. When you measure it on standard benchmarks, it's currently comparable to non-private models from about 5 years ago. Think something like GPT-2.
Okay, so like 2019, 2020 era performance?
Roughly, yeah. But, and this is crucial, the performance trade-off absolutely shouldn't obscure its profound significance. VaultGemma is a vital proof of concept. It demonstrates that inherently safe AI isn't just some abstract ideal. It's an achievable engineering reality.
So, VaultGemma, 1 billion parameters. Google AI Research, DeepMind, we got that. But you called it a landmark. That implies something, well, much deeper than just its size, right? What's the core innovation here? What really sets it apart?
It's landmark precisely because it's the largest open-weight LLM built from the ground up, from scratch, with these mathematically rigorous differential privacy guarantees. I mean, think about the usual approach.
Yeah.
Often people try to, de-identify data before training, or maybe add some privacy filters after the model's built.
Right, reactive measures.
Exactly, reactive. VaultGemma just throws that playbook out. This is fundamentally privacy by design. Privacy is baked into its DNA from the very first training step. And the core technology enabling this, it is an advanced implementation of something called Differentially Private Stochastic Gradient Descent, DP-SGD.
DP-SGD, okay, that's a mouthful.
It is. But basically, it's a clever algorithm that doesn't just filter data. It strategically injects carefully calibrated statistical noise throughout the entire training process. It fundamentally changes how the model learns. And because of this deep integration, it becomes mathematically improbable, really, really unlikely, that the model's outputs could ever be traced back to one specific piece of training data.
Mathematically improbable, not just unlikely.
Exactly. It's not just a promise, it's a verifiable outcome. And this is the critical part we mentioned. Empirical tests confirmed zero detectable memorization. Zero. Which is a stark contrast, frankly, to how many powerful, non-private models behave today. Researchers have shown repeatedly they can extract verbatim training data from those.
That privacy guarantee sounds incredible, a real game changer. But you used that phrase again, privacy tax. Can you unpack that a bit more? It definitely sounds like a trade-off is happening.
You've hit on the key point there. Yes, there is an unavoidable, quantifiable trade-off in performance. That is the privacy tax.
Hmm.
When we measure VaultGemma against standard academic benchmarks, tests for reasoning, question answering, things like that, its overall utility, how well it performs, it's comparable to non-private models that were cutting edge maybe 5 years ago, like GPT-2.
Okay.
Now, this comparison, it isn't meant to diminish VaultGemma at all. It's actually a really vital point of reference. It establishes a clear public baseline for the community. It shows us, concretely, the current state of that privacy utility trade-off in large-scale AI.
So it basically quantifies the cost.
Precisely. It tells us in real numbers what you currently pay in raw performance points to get these incredibly strong mathematical privacy guarantees. It's like an investment in trust, and now we know the initial price.
And you also mentioned these DP scaling laws that came with the model release. They sound like more than just a technical footnote. Are they a big deal too?
Oh, absolutely. You could argue these scaling laws are just as transformative as VaultGemma itself, maybe even more so for the wider AI community. See, traditional AI development relies heavily on scaling laws that predict how models get better with more data, more compute power, bigger size.
Right, there's predictable curves.
Exactly. But DP throws a wrench in that. The noise injection changes everything. Those old rules just don't apply anymore. So these new DP scaling laws developed by Google, they represent a completely novel framework. They meticulously model the complex dance between compute, the level of privacy you want your privacy budget, and the resulting model performance. What this does is transform private model development. It takes it from being, honestly, a bit of an art form, lots of trial and error.
Guesswork, almost.
Yeah, almost guesswork, very empirical. And it turns it into a structured, predictable engineering discipline. And by open sourcing not just VaultGemma's weights, but also these crucial scaling laws on Hugging Face, on Kaggle, Google's providing a foundational toolkit. It's more than just a model, it's a blueprint designed to seriously accelerate community research. So VaultGemma right now, it's not about topping the leaderboards for raw performance. Its role is much more profound. It's the proof of concept. It shows how we can build powerful AI that is inherently safe, transparent, and trustworthy, built on solid privacy foundations.
Okay, this really gets to the heart of the problem VaultGemma is solving. Why is this whole memorization issue such a big deal for these large language models, especially as they get more powerful and train on just unbelievable amounts of data?
Well, the incredible power these LLMs have generating text, answering questions, writing code, it comes directly from being trained on truly colossal data sets. Web-scale data, trillions of tokens.
Trillions, it's hard to even comprehend.
It really is. But that very process, training on so much diverse data, is exactly what makes them vulnerable to what researchers call memorization attacks, or sometimes extraction attacks. Essentially, the model can inadvertently store or memorize specific, often unique sequences of text it saw during training.
Like photographic memory, almost?
Sort of, but unintentional and patchy. The real danger comes when, if you give it the right prompt, the model can just regurgitate those memorized sequences, verbatim, word for word. So imagine an LLM trained on, say, a mix of public websites and maybe some internal company documents.
Yeah.
If a rare, sensitive piece of information, maybe a specific patient diagnosis from a forum or a unique customer ID from a support log was in that training data, even just once, the model could potentially spit out that exact detail later, maybe in response to a completely unrelated question.
Oh, okay.
And that directly leads to the potential exposure of sensitive information, PII, personally identifiable information. It creates a massive liability. And numerous studies, really solid research, have consistently shown this isn't just theoretical. Verbatim data extraction is possible, especially from many of the popular open-weight models people use.
So it's a proven risk.
A proven risk, and it acts as this formidable barrier, this wall, preventing wider LLM adoption in highly regulated industries. Think healthcare, with hypo mandating patient confidentiality, or finance, where client data privacy is absolutely sacred, or even legal services dealing with privileged information.
They just can't take that risk.
Exactly. The risk of unintended data leakage means these industries have been, quite understandably, very hesitant to fully embrace the latest LLM technology. VaultGemma was conceived specifically to tackle this foundational challenge head-on. The goal was to build a model that is provably incapable of this kind of dangerous memorization.
Now, here's something that could definitely trip people up. A crucial point of clarification. VaultGemma shares part of its name with Google Vault. Are these related? Are they two sides of the same coin, or are we talking about completely different things here?
That's an excellent question, and yet it's really important to disambiguate these. While both names clearly evoke security, protection, keeping things safe, they are fundamentally distinct technologies. They operate on different principles. They serve entirely separate functions within Google's wider ecosystem. You can almost think of them as two different kinds of vaults protecting different things in different ways.
Okay, break it down for us.
Right. So Google VaultGemma, the focus of our chat today, it's a generative AI model, came out of Google's AI research divisions, part of the Gemma family of open models. Its defining feature, its whole reason for existing, is that it's trained from the ground up using differential privacy. That gives it these proactive algorithmic guarantees specifically against data memorization. Its job is to generate text while mathematically ensuring the privacy of the data it learned from.
So it prevents a new kind of risk, the AI memorization risk.
Precisely. It's proactive. Now contrast that with Google Vault. That's an information governance and e-discovery tool. It's a key part of the Google Workspace suite, Gmail, Drive, etc. Its purpose is completely different. It helps organizations retain, hold, search, and export user data from those Google services. Why? Mainly for compliance, legal regulations, industry standards, internal policies, and for handling e-discovery requests during lawsuits.
So it's about managing existing data archives.
Exactly. Google Vault is reactive, it's policy-driven, it's about managing the data you already have. It's not an AI model generating new stuff, it's for your digital filing cabinet, essentially.
Okay, that distinction is crystal clear. One prevents a new AI risk, the other manages existing data for compliance. So how do these two seemingly different vaults actually complement each other? Is there synergy?
There absolutely is, and that's likely why the branding shares the Vault name. They represent two distinct but highly complementary pillars of a really comprehensive enterprise data governance strategy. Think about it. Google Vault is reactive. You use it to make sure your existing data is properly archived, discoverable if legal needs arise, compliant with rules. VaultGemma, on the other hand, is profoundly proactive. It's purpose-built to prevent the creation of a new risk, an AI model leaking sensitive stuff it learned. So picture an enterprise. They might need to use Google Vault to put a legal hold on some highly confidential internal project documents. Standard procedure. Now, they could potentially take those exact same documents and use them to fine-tune a VaultGemma model. Why? To create a specialized internal knowledge assistant, maybe, that understands the confidential project details? But here's the key. VaultGemma provides that mathematical assurance that this powerful new AI tool cannot be prompted to leak the confidential information it was trained on, even highly sensitive stuff.
So you can manage the data and use it safely for AI.
Precisely. This dual approach lets an organization diligently manage its existing data for legal and compliance needs and safely leverage that very same data for cutting-edge AI-driven innovation. It creates a much more holistic, robust data governance posture for the modern age. Hashtag 1.4, situating VaultGemma in Google's multi-layered security ecosystem.
So VaultGemma isn't operating in isolation then. It's part of a much bigger picture, a multi-layered security strategy at Google. How does it actually fit in? What other technologies does it work alongside to protect AI and cloud workloads?
That's a crucial perspective to have. VaultGemma is definitely not a standalone silver bullet. It's designed to be a critical, synergistic piece within Google's broader defense and depth strategy for securing both AI and general cloud workloads. Think of it like one really important layer in a sophisticated security onion. It works hand in hand with other major security technologies and also conceptual frameworks that Google offers. Together, they create a much more robust, multi-layered defense against a whole range of potential threats.
Okay, like what other layers?
Well, consider something like Google Cloud's confidential computing. This includes services like confidential VMs, confidential space. What these do is focus on protecting data while it's being used.
Data in use. How?
It encrypts the data while it's loaded in memory inside a special hardware-based secure zone called a Trusted Execution Environment, or T. This T acts like a secure black box. It isolates the data and the computation, preventing unauthorized access during processing, even, theoretically, from the cloud provider itself or privileged system admins. So it secures the environment where the computation happens.
Okay, that secures the runtime. What else?
Then there's Google's Secure AI Framework, or SAIF. Now, this isn't a specific product you buy. It's more of a conceptual framework, a set of best practices and guidelines. SAIF is meticulously designed to help organizations build and deploy AI systems responsibly and securely. It really emphasizes integrating security and privacy thinking throughout the entire AI development lifecycle, from the very beginning, initial design, data collection, all the way through deployment and ongoing monitoring. It's the strategic overlay.
Got it. So confidential computing protects the environment. SAIF is the blueprint. How do these different pieces, specifically VaultGemma, confidential computing, and SAIF, all work together? What does that comprehensive protection look like in practice?
You've got the pieces exactly right. They are distinct, but their synergy is where the real power lies. Confidential computing, like we said, ensures the runtime environment is locked down, shielding the data and the computations while they're active. But here's the catch. A standard LLM, even if it's running inside a super secure confidential VM, could still theoretically memorize sensitive data it processes and then potentially leak that data later through its outputs. The environment is secure, but the model itself might still be leaky.
So confidential computing doesn't solve the memorization problem itself.
Exactly. And that's precisely the risk VaultGemma was built to mitigate. Its differential privacy guarantees ensure that the model artifact itself, the trained model weights, is inherently private with respect to its training data. It makes the model fundamentally resistant to memorization, regardless of the environment. So, by combining these, you get end-to-end security. Imagine a bank, a highly regulated financial institution. They could choose to fine-tune a VaultGemma model on their sensitive customer transaction data.
Okay.
They could run this fine-tuning process inside a confidential VM. The VM protects the training process at the infrastructure level, shielding the raw data while it's being used. And, critically, VaultGemma's DP-based training ensures the final fine-tuned model cannot leak that sensitive customer data it learned from. It provides a mathematical assurance against memorization, and the entire process from start to finish would be guided by the principles of Google's Secure AI Framework, SAIF, ensuring security and privacy are integrated from the outset, not just bolted on.
Wow. Okay, that's a really sophisticated, multi-layered approach. It shows a deep understanding of the different threats.
It really does. It acknowledges that security isn't just one thing. It's a property woven throughout the entire system, from the hardware up to the model itself, guided by a strong strategic framework.
Okay, let's really get into the weeds now with the core technical marvel here. Differential privacy. We hear this term thrown around a lot, especially in data security circles, but what does it actually mean to have a mathematical guarantee of anonymity when you're talking about something as complex as an AI model learning from potentially trillions of data points?
Yeah, DP is definitely more than just a buzzword. It's a formal mathematical framework, and it's widely seen as the gold standard for privacy-preserving data analysis precisely because it provides these incredibly rigorous, provable guarantees. Guarantees that go way beyond what you get from older ad hoc methods like just trying to remove names or blur faces. Those often fail against determined attackers. The core idea behind DP, while mathematically precise, is actually quite intuitive. It says that the output of a differentially private algorithm like the trained VaultGemma model should not significantly change if you add or remove any single individual's data from the input data set used to train it.
Not significantly change. Okay, what does that mean practically?
Practically, it means that if someone observes the algorithm's output, say, they interact with VaultGemma, they cannot confidently determine if your specific information was included in the training data or not, even if they're a super sophisticated adversary with lots of background knowledge. This gives every individual whose data might have been used what's called plausible deniability.
Plausible deniability. I like that.
It's a powerful concept. It effectively protects individuals against a range of nasty privacy attacks. Things like reconstruction attacks, where someone tries to recreate the original sensitive data, or membership inference attacks, where they try to figure out if your data was even in the training set to begin with. DP guards against both. Formally, mathematically, DP is defined by an inequality involving two key parameters, epsilon, that's AOS, and delta. These two numbers quantitatively measure the maximum privacy risk any single individual incurs by having their data included. And the beauty of it is this guarantee holds true regardless of what other information an attacker might have or how much computing power they throw at the problem.
Okay, epsilon and delta. You mentioned these are the parameters that quantify the privacy strength. Can you break those down a bit more? How should we think about A + B?
Absolutely. Think of the epsilon parameter, often called the privacy loss, as measuring how much the algorithm's output distribution can change due to any single individual's data. A smaller A value means a stronger privacy guarantee. It means the outputs are more indistinguishable whether or not your data was included. It's like having a tighter seal on privacy.
So lower epsilon is better privacy.
Generally, yes. A larger epsilon allows for potentially more accurate or useful results from the algorithm, but it comes at the cost of a weaker privacy guarantee, a looser seal. For VaultGemma, they aimed for a strong guarantee, achieving an AT of less than or equal to 2.0. That's considered a pretty robust and meaningful level of privacy in the research community.
Okay, and what about the delta?
All right, delta. This parameter represents the probability that the strict A privacy guarantee might be broken. You can think of RA as the very, very small chance that the privacy promise fails catastrophically for a specific instance. For DP to be meaningful must be an extremely small number, typically much smaller than 1 divided by the size of the dataset. VaultGemma achieved an incredibly small J, less than or equal to 1.1 times 10 to the minus 10.
Wow, that's tiny.
It's exceptionally tiny. It means the privacy guarantee is extremely reliable. The probability of that strict epsilon guarantee failing is practically negligible.
So smaller numbers for both area and D mean a tighter, more reliable privacy shield. That makes sense. But you also mentioned a privacy unit for VaultGemma. What does that mean in practical terms for someone using the model?
That's a really important nuance. VaultGemma's DP guarantee is provided at the sequence level. What does that mean? It protects any single 1024 token sequence, that's the context window length we talked about, in its training data from being memorized and revealed. This is a very natural unit for text data, since LLMs process text in these fixed-length chunks or sequences. However, there's a crucial implication here.
Which is?
If the same fact or the same piece of information happens to appear across many different distinct sequences within the overall training data, the model can still learn that fact and report it.
Ah, okay. So if the CEO is Jane Doe, appears in 50 different documents.
Exactly. Even if each of those 50 sequences is individually protected by DP, the model can still learn the aggregate fact that the CEO is Jane Doe. It won't be able to tell you which specific document it learned it from because each sequence is protected, but the repeated fact itself can become public knowledge through the model's outputs.
I see. So it protects the source, but not necessarily facts that appear multiple times.
That's a good way to put it. That's why moving towards what's called user-level DP is a major goal for future research. User-level DP would aim to protect all data associated with a single user, no matter how many sequences it spans. That provides a stronger, more intuitive guarantee, but it's significantly more challenging to achieve, especially at the scale of models like VaultGemma.
So we have this really elegant mathematical definition of privacy with epsilon and delta, but how do you actually translate that into the nuts and bolts, the practical process of training a massive neural network like VaultGemma? It's constantly adjusting potentially billions of parameters based on trillions of data points. It sounds incredibly complex to inject privacy into that.
It is indeed a significant engineering feat. It's a sophisticated dance between ensuring the model learns effectively and ensuring it does so privately. To apply differential privacy during the training of these large neural networks, Google used a specialized algorithm we mentioned earlier. Differentially private stochastic gradient descent, or DP-SGD. DP-SGD cleverly modifies the standard stochastic gradient descent process, which is really the workhorse algorithm for almost all deep learning in 2 absolutely critical ways. These modifications ensure privacy during every single update the model makes to its internal weights.
Okay, 2 modifications. What's the first one?
The first modification is gradient clipping. Okay, so in each training step, the model calculates a gradient. Think of the gradient as a direction. How should I adjust my weights to reduce my error on this piece of data? Well, normally you'd calculate this for a batch of data and average them. With DP-SGD, you first compute this gradient for every single individual example within the batch. Then, before combining them, you measure the size or magnitude of each individual gradient. Technically, it's L2 norm. And if any individual gradient is too large, larger than a predefined threshold, you clip it. You essentially scale it down so its magnitude is capped at that threshold.
Like putting a speed limit on how much influence one data point can have.
That's a perfect analogy. Gradient clipping puts a strict limit on the maximum influence any single data point, especially an unusual or outlier one, can have on the overall direction the model takes in that step. This is crucial because without clipping, a very unique data point could create a huge gradient, potentially revealing too much specific information about itself in the model update. Clipping tames these potentially loud voices, preventing them from disproportionately affecting the model's weights and thereby protecting the privacy of that specific data point.
Okay, so clipping limits individual influence. What's the second modification?
The second, equally vital modification is noise injection. After all the individual gradients in the batch have been clipped, they are then averaged together to get a combined update direction. Then, before the model actually uses this average gradient to update its weights, a carefully calibrated amount of random noise is added directly to it. This noise is typically drawn from a mathematical distribution, like a Gaussian distribution.
Adding noise. That sounds counterintuitive for learning.
It seems like it, but this noise is the absolute heart of the privacy guarantee. Think of it like adding a bit of carefully controlled static or fuzziness to the aggregated update signal. This injected noise masks the precise contribution of each individual example that went into that batch average. It makes it statistically impossible, or at least improbable according to the epsilon delta guarantee, for an adversary looking at the model's updates over time to reverse engineer things and figure out if your specific data point was included in any particular batch. The amount of noise added isn't random guesswork either. It's meticulously chosen, mathematically linked to the clipping threshold and the target privacy level, those and O values we talked about, to precisely achieve the formal DP guarantee.
Okay, so clipping limits the impact, and noise hides the individual traces within the group average. And this whole process, clipping, then noise injection, happens for every single batch, every single update, throughout the entire massive training run.
Precisely. This meticulous two-step process clip each individual, average the clipped individuals, then add noise to the averages repeated over many, many thousands, potentially millions, of training iterations. Each step contributes incrementally to the overall privacy guarantee. The privacy accounting carefully tracks the cumulative privacy cost across all these steps. This ensures that the final model, the end product of all this training, carries a rigorous, mathematically accounted for privacy guarantee. It fundamentally builds privacy into the model's learning process from the ground up. It's not an add-on, it's integral.
Let's get into the specifics now, the actual design of VaultGemma. What's really under the hood of this private LLM? How was its architecture chosen or maybe even modified specifically to handle this demanding DP training regime we've been talking about? Because it sounds like DP places some serious constraints on things.
Right. The architecture choices were definitely influenced by the needs of DP training. VaultGemma's core architecture is based on the Gemma 2 family, which means it's a decoder-only transformer, a very common and effective design for generative AI these days. However, there were specific modifications and design choices made to optimize it for the rigors of DP-SGD. It's a substantial model for the world of privately trained AI, clocking in at approximately 1 billion parameters. These parameters are distributed across 26 layers in the neural network.
Okay, 1 billion parameters, 26 layers. What about the attention mechanism? That's usually key in transformers.
Good question. It uses something called multi-query attention, or MQA. This is a clever optimization. Instead of each attention head having its own set of key and value projection matrices, in MQA, all the heads within a layer share a single set.
And why is that helpful?
It significantly reduces the memory footprint and the computational cost, especially during inference, when the trained model is actually generating text or predictions. This efficiency is vital generally, but it's particularly valuable for a DP-trained model. It helps to make the final model more broadly accessible and efficient to deploy, which can help offset some of that privacy tax we discussed when it comes to actually using the model in the real world.
Makes sense. Now, you mentioned earlier it has a context window of just 1,024 tokens. That really does seem shorter than many of the huge LLMs we hear about now, boasting context windows tens or even hundreds of thousands of tokens long. Was that just a limitation, or is that a strategic choice driven by the privacy requirements?
That was absolutely a deliberate and indeed crucial strategic trade-off made specifically for DP training. While yes, it is shorter than some non-private contemporary models, having a smaller sequence length dramatically lowers the computational and memory requirements for each individual training example.
Okay. And why is that so important for DP?
Because, as we discussed, DP-SGD requires extremely large, effective batch sizes to overcome the injected noise and allow the model to learn effectively. By making each individual training example computationally cheaper, because it's shorter, you can afford to process many, many more of them together in a single effective batch.
I see. Shorter sequences enable the massive batches needed for DP utility.
Exactly. It's a key enabler. Now, to make sure the model is still effective, even with this shorter 1024 token context, they use global attention across all layers. This means every token in that window can still attend to every other token, maximizing the use of that context. They also made other architectural choices for stability in the noisy DP environment, like using RMS norm normalization in a pre-norm setup, and employing GGLU activation functions in the feed-forward layers. These are technical details, but they point to careful engineering for robust learning under DP constraints.
Okay, so that's the architecture. Where did VaultGemma actually learn from? What was the training data? And critically, how was that data handled before the DP training even started? Because surely the quality and initial privacy of the raw data must matter a lot too, right?
Absolutely. Data quality and meticulous preprocessing are foundational. You can't build a good safe house on shaky ground, right? Same applies here. VaultGemma was trained on the same extensive high-quality data set that was used for the larger, non-private Gemma 2 models. This is a massive corpus, 13 trillion tokens of text.
13 trillion?
Trillion with a T. It's primarily English-language text sourced from a diverse mix of public web documents, vast amounts of computer code, scientific articles, and other sources. But crucially, this dataset didn't just get fed straight into the DP training pipeline. It underwent a rigorous multi-stage filtering process first. This pre-processing wasn't just about basic cleaning. It was meticulously designed to enhance the safety, quality, and the initial privacy posture of the data before DP even came into play.
So layers of protection, starting with the data itself. What did the filtering aim to do?
It had several key goals. First, it aimed to remove unsafe, toxic, or otherwise undesirable content that could lead to harmful or biased model outputs. That's standard responsible AI practice. Second, it worked to significantly reduce the presence of personally identifiable information, PII, and other kinds of sensitive data that might still be learning, even in publicly available web data, trying to minimize that from the start. And third, a really important step for research integrity was decontaminating the training set. This means removing any data that might accidentally overlap with common evaluation benchmarks the tests use to measure the model's performance later. This ensures the performance measurements are fair and unbiased, not just reflecting memorization of the test questions.
Got it. So a huge effort on data quality, safety, and preliminary privacy before the heavy machinery of DP-SGD even got switched on.
Exactly. Privacy and safety were considered in multiple stages, from the painstaking data curation and filtering right through to the sophisticated DP training algorithm itself.
Okay, implementing DP-SGD at this kind of scale, 1 billion parameters, 13 trillion tokens, those intense mathematical guarantees, it sounds like an engineering nightmare, frankly. How did the teams at Google actually translate those complex theoretical principles into a functional performant training system that could handle this massive load without, falling over or taking centuries?
It was absolutely a monumental engineering undertaking, no question. It required highly optimized, highly scalable software and hardware working in concert. The theoretical principles of DP-SGD were translated into a sophisticated, production-grade implementation. This was built primarily using JX, which is Google's high-performance numerical computing library, particularly well-suited for TPUs, and they leveraged key components from the JX privacy library, which provides these optimized building blocks specifically designed for implementing differential privacy algorithms efficiently.
So the specialized tools were key. What kind of optimization techniques did they need?
Several techniques were absolutely essential to make DP training feasible at this scale. One we touched on implicitly was vectorized, for example, clipping. Remember how we need to clip the gradient for each example? Doing that one by one would be incredibly slow. So they vectorized this operation. This means the TPUs could process the gradient clipping calculations for multiple examples simultaneously, in parallel across their many cores. That massively speeds up this critical privacy step.
Okay, parallel processing for clipping. What else?
Another absolutely critical technique was gradient accumulation. We keep talking about needing massive effective batch sizes for DP, right? Maybe hundreds of thousands of tokens. But fitting all that data and its corresponding gradients into the physical memory of the chips at once is often impossible.
Right, you'd run out of RAM.
Exactly. So with gradient accumulation, you do multiple smaller forward and backward passes to the model, calculating gradients for smaller chunks of data. But instead of updating the model weights after each small chunk, you just accumulate or sum up these gradients over several passes. Only after accumulating gradients from enough chunks to reach your massive target effective batch size do you perform a single weight update.
Ah, so it simulates a giant batch without needing all the memory at once. Clever.
Very clever and absolutely essential for DP at scale. And a third key piece was using truncated Poisson subsampling for selecting the mini batches. This is a specific computationally efficient way to randomly sample the data points for each batch. Crucially, it's also privacy accountable. It allows the engineers to precisely track the probability with which each individual data point was selected for training. This precise tracking is a fundamental requirement for correctly calculating the overall privacy loss epsilon and delta, accumulated throughout the entire training process. It was integrated right into the data loading pipeline.
Wow. Vectorized clipping, gradient accumulation, privacy accountable sampling. It really highlights how much specialized engineering goes into making DP practical at this scale.
It absolutely does.
Yeah.
The marriage of deep theoretical understanding of DP and cutting-edge large-scale systems engineering.
You mentioned TPUs there. Training an LLM is already computationally intensive. Training one with differential privacy, with all that extra work, for example, gradients, noise injection, massive batches, sounds incredibly demanding. What kind of hardware infrastructure was actually needed? Could this have been done on, say, a large cluster of standard GPUs, or are TPUs really necessary here?
That's a great question. And the computational demands are indeed substantially higher for DP training compared to standard LLM training. All those extra steps we discussed, the, per example, gradient calculations needed for clipping, the potential overhead from noise generation, and especially the necessity of using those extremely large effective batch sizes, they create significant computational overhead. This makes specialized AI accelerators not just helpful, but pretty much indispensable for doing this kind of work at the scale of VaultGemma efficiently.
So TPUs were essential.
For this project, yes. VaultGemma was trained on a truly formidable cluster. 2048 tensor processing unit chips, specifically the TPU V6E generation. Google's TPUs are custom-designed processors, purpose-built ASICs, optimized specifically for the massive matrix multiplications and other operations that dominate deep learning workloads. They have features like very high memory bandwidth and specialized interconnects that make them particularly well-suited for the unique demands of DP-SGD. They handle those large batch sizes and complex gradient operations very efficiently.
So could it have been done on GPUs?
Theoretically, maybe, given enough time and a vast number of GPUs. But practically, it would likely be far slower and much more expensive. The specific architecture of TPUs really lends itself well to the kinds of operations needed for DP-SGD at this scale. It enables training models like VaultGemma at 1 billion parameters with strong DT guarantees on a timescale and budget that would be incredibly challenging, if not entirely impractical, using more general-purpose hardware like GPUs.
So the specialized hardware was really a key enabler for making VaultGemma a reality.
Absolutely. Without that kind of dedicated, specialized compute infrastructure, pushing the boundaries of private AI training to this billion-parameter scale would have been vastly more difficult, perhaps even unattainable within reasonable research timelines and resource constraints.
Okay, for our listeners who really love the technical details, the hard numbers, could you give us a quick rundown, like a snapshot of VaultGemma 1B's key specifications? What are the core stats that define this model?
Certainly. Let's consolidate the highlights, the key specs that really characterize VaultGemma 1B. First off, parameters. It has approximately 1.04 billion trainable parameters.
Okay, 1 billion.
Architecture type. It's a decoder-only transformer based on the efficient Gemma 2 family blueprint. It has 26 layers and utilizes multi-query attention MQA for better inference efficiency.
MQA, right.
Context length. Trained with a 1024 token context window, that deliberate choice we discussed to enable large batches.
1K context, got it.
Training data set. An immense 13 trillion tokens of primarily English text sourced from web documents, code, and scientific articles after rigorous filtering.
13 trillion tokens.
Wow. DP guarantee. Epsilon.
Yeah.
It achieves a strong privacy guarantee with EPS 2.0. Remember, lower epsilon is generally better privacy.
Epsilon less than or equal to 2.
DP guarantee,
Right.
delta, and an extremely reliable guarantee with 1.110. That's an incredibly small probability of failure.
Delta extremely tiny. Okay.
Privacy unit. The guarantee applies at the sequence level, protecting each 10124 token chunk.
Sequence level privacy.
Training hardware. Trained on a large cluster of 2048 TPU VA6E chips.
Over 2,000 TPUs.
Effective batch size. This hardware enabled a massive effective batch size of approximately 518,000 tokens, crucial for DP utility.
500,000 token batch size. Incredible.
And finally, availability. Crucially, it's released with open weights. The model is freely available on platforms like Hugging Face and Kaggle for the community.
Open weights. That's key. Great summary. This brings us to another really fascinating piece of the VaultGemma story, these new scaling laws. Now, in the non-private AI world, scaling laws have been incredibly powerful, almost like cheat codes, right? They predict how a model will perform based on its size, the data, the compute. But you mentioned earlier, those old rules just break down when you introduce differential privacy. Why is that? Why doesn't the old playbook work here? It really sounds like DP introduces entirely new physics for AI training.
A whole new physics is a great way to think about it, because the introduction of differential privacy, specifically the mechanisms like DP-SGD, fundamentally alters the training dynamics. It renders those traditional scaling laws, which have been so incredibly useful for guiding non-private AI development, like the chinchilla scaling laws, for instance, not just a bit inaccurate, but largely inapplicable. It's like trying to use Newtonian physics to predict quantum tunneling. The underlying principles have changed. The constant, deliberate injection of noise during DP-SGD, which we know is essential for the privacy guarantee, has two major disruptive effects that completely reshape how the model learns.
Okay, two effects. What are they?
Firstly, as we touch upon, it significantly reduces training stability. Imagine trying to steer a ship in constantly choppy waters. The noise introduces turbulence into the learning process. This increases the risk of loss spikes, where the model's learning progress suddenly goes off track, its error jumps up, and stable convergence becomes much harder to achieve.
More unpredictable training.
Exactly. And secondly, and this is critically important for scaling, it creates a significantly increased requirement for the batch size. Remember, the noise dampens the learning signal from individual examples. It's like trying to hear whispers in a very noisy room. To get a clear, stable gradient update, a reliable direction for the model to learn, you need to average over many, many more examples in each step. You need a much larger crowd to discern the collective signal through the background noise.
So bigger batches are needed just to overcome the privacy noise.
Precisely. These two factors reduce stability, and the need for massive batches create an entirely new, much more complex trade space. You're now juggling compute, privacy level, epsilon delta, model utility performance, data size, model size, and batch size in a way that traditional scaling laws simply weren't designed to handle. They don't account for the noise of the specific mechanisms of DP, hence the need for a completely new approach, a new set of laws. Hashtag tag 4.2, Google's 3 innovations for deriving DP scaling laws.
So if the old rules are out the window, Google basically had to invent a whole new way to predict how private AI models will behave. They had to write a brand new playbook for scaling private AI. That sounds incredibly ambitious given all that complexity. How did they actually manage to do it? What were the key breakthroughs or innovations that allowed them to derive these new DP-specific scaling laws?
Exactly. They recognized the need for a new playbook and developed a really novel methodology to create it. The Google Research and DeepMind teams came up with 3 key innovations that were crucial for efficiently and accurately deriving these DP-specific scaling laws in this challenging new domain.
Okay, 3 innovations. Let's hear them.
First, they developed a method for explicit modeling of the optimal learning rate. Finding the best learning rate, how big the steps the model takes during learning should be, is critical. Traditionally, you might do expensive grid searches, trying lots of different values. They figured out a way to model the optimal learning rate as a quadratic function of the other training parameters like noise level, batch size, etc. This allowed them to predict the best learning rate much more efficiently, avoiding those costly trial and error searches and saving enormous amounts of compute time.
Smart. Predicting the best settings instead of searching for them. What was the second innovation?
Second was something called parametric extrapolation of loss values. Training these huge models, especially with DP, takes a long time and costs a lot. Running hundreds of full training runs just to map out the scaling behavior would be prohibitively expensive. So they developed a clever mathematical trick. They used a specific type of parametric function to fit the model's loss curve, how its error decreases, based on data from only shorter initial training runs. This function could then accurately extrapolate or predict what the final loss would likely be if the training continued for many more iterations.
So they could predict the end result without running the whole race?
Exactly. It dramatically reduced the computational cost needed to explore the vast space of possible training setups because they could get reliable estimates of final performance from much shorter, cheaper experiments.
Very efficient. And the third innovation?
Finally, they used a semi-parametric fit for the final scaling law itself. This was a 2-stage process. First, they used a parametric model, simpler, based on assumed relationships, to capture the main trends in loss based on things like model size and the number of training steps. Then they took the outputs or predictions from that initial model and used them to train a more flexible, non-parametric model, like a Gaussian process. This second stage could capture the more subtle, complex interactions, accurately predicting the final loss for almost any combination of model size, training steps, and crucially that unique DP factor, the noise-to-batch ratio. This combined approach gave them both structure and flexibility, allowing for highly accurate predictions across the complex DP training landscape.
Wow. Explicit learning rate modeling, parametric extrapolation, semi-parametric fitting. That's some serious statistical and machine learning ingenuity applied just to understand how to train these things better.
It really is. It was necessary to turn the art of DP training into more of a predictive science.
This feels like a really pivotal moment in understanding how to build private AI effectively. With all that incredibly complex modeling and those clever innovations, what's the single most critical, most actionable insight that came out of these new DP scaling laws? What's the bottom line, the big takeaway for anyone trying to build privacy-preserving AI?
This is indeed the core revelation, the punchline, if you will.
Mm-hmm.
And it's fascinating because it directly contradicts a lot of the prevailing wisdom from the non-private AI world, the genuinely counterintuitive truth. The scaling laws demonstrate definitively for a fixed amount of computational resources, a fixed compute budget, under the constraints of differential privacy, the optimal strategy is often not to train the absolute largest model you possibly can, which is usually the mantra in non-private AI: bigger is better.
Right, go big or go home.
Exactly. But with DP, the optimal path, according to these laws, is frequently to train a smaller model but run the training for more iterations, more steps, and crucially, use a much, much larger effective batch size than you would typically choose without DP.
Smaller models, but way bigger batches. Why? What's the intuition there?
The intuition goes back directly to the noise. The noise inherent in DP training makes the learning signal weaker and more erratic. A huge model with billions of parameters might simply have too much capacity, too many knobs to tune to learn effectively when the information it's getting is constantly being obscured by that privacy-preserving noise. It struggles to find a clear path. A smaller model with fewer parameters to adjust can actually converge more reliably and learn more efficiently in that noisy environment. It can find the signal through the static more easily. And the importance of the batch size here just cannot be overstated. It's absolutely critical for making DP work well. Remember VaultGemma, trained with an effective batch size of around 518,000 tokens.
500,000, yeah.
That massive scale was necessary precisely to ensure that the aggregated gradient signal, averaged over that huge number of examples, was strong and clear enough to overcome the blurring effect of the injected privacy noise. It allows the model to learn meaningful patterns while still providing those strong mathematical privacy guarantees. It's a complete inversion of the typical non-private strategy of often favoring larger models and sometimes smaller, faster batches. DP demands scale and batch size, often favoring smaller model size for a given compute budget.
That is a profound shift in thinking. So what does all this mean practically for other researchers, for companies, for organizations around the world who are looking to build their own private AI systems? It sounds like Google didn't just release VaultGemma. They effectively published a detailed roadmap, a guidebook on how to navigate this new territory efficiently.
You've absolutely nailed the significance there. The public release of these DP scaling laws is arguably just as transformative for the field as the VaultGemma model itself, maybe even more so in the long run. It provides the broader AI research community with something that was sorely lacking: a validated, predictable, and repeatable roadmap for developing large-scale private AI. This is a monumental contribution because before this, developing private LLMs was often this painstaking, resource-intensive process of trial and error. It felt like alchemy sometimes. It was really only accessible to groups with immense computational resources and deep specialized expertise in DP.
It was a bit of a black art.
Exactly, a black art. Now, with these laws, practitioners anywhere can leverage them. They can now accurately estimate the computational resources they'll need to reach a specific target level of performance, utility, for a given privacy budget, epsilon delta. They can determine the optimal model size and batch size for their specific hardware constraints and budget, avoiding costly dead ends and wasted experiments. And remarkably, they can forecast the likely achievable loss, the model's final error rate, before even starting a full-scale, expensive training run.
That's huge. Predictability.
It's huge. The fact that VaultGemma's own final training loss was within just 1% of what these scaling laws predicted beforehand is incredibly strong validation of the methodology. This effectively demystifies the entire process. It makes private AI development more accessible, much more efficient, and crucially, it accelerates collective progress in the field by transforming it from guesswork into a structured, predictable engineering challenge that more people can participate in. It's a democratization of private AI development.
Okay, so we've established VaultGemma is private. Demonstrably so, with those rigorous mathematical guarantees and the engineering to back it up. But the big question hanging in the air for many listeners will be, How does it actually perform? How smart is it? How capable? Is there a massive hit to its utility because of the privacy? Is that privacy tax you mentioned so steep that it makes the model less useful in practice?
Right. The evaluation phase is all about quantifying that exact trade-off, putting numbers on the privacy tax so we can have an honest discussion about the real-world implications. To give us that crucial context, VaultGemma was rigorously benchmarked against two key comparison points. First, its non-private contemporary sibling, Gemma 3.1b, which uses a similar architecture but without DP. And second, a historically significant model of roughly similar size, GPT-2 1.5v, which represented the state-of-the-art around 2019-2020. This three-way comparison helps us see both the cost of privacy relative to today's non-private tech and its utility compared to high-performing AI from the recent past.
Okay, so how did it stack up?
Well, the results clearly show the privacy tax is real. On challenging benchmark tasks like ARCC, that's science reasoning, and Trivia QA, broad general knowledge question answering, VaultGemma's scores are noticeably lower than the non-private Gemma 3.1b. That's the direct measurable cost of integrating DP so deeply.
So, a definite performance hit compared to its non-private twin.
Yes. However, and this is where it gets really compelling and frankly quite impressive given the strong privacy. Look at the comparison with GPT-2 across several other standard benchmarks like PIQA, common sense reasoning, and BullQ, yes-no factual questions. VaultGemma's performance is either right on par with, or in some cases even slightly better than, the GPT-2 1.5b model.
Wait, really? So while it's not matching the absolute cutting edge of today's non-private models, it's performing roughly at the level that was considered genuinely high-performing just a handful of years ago. That sounds actually quite practical.
Exactly. That finding is absolutely crucial because it completely reframes how we should think about the privacy tax. Yes, DP training imposes a quantifiable cost compared to the absolute bleeding edge of non-private LLMs today, but the resulting model is far from being just a toy or a purely academic exercise. Its utility level is roughly equivalent to what was considered powerful, high-performing AI around the 2019-2020 timeframe. This establishes a vital public baseline. It tells us the tangible cost of privacy right now, but more importantly, it frames the existing utility gap not as an insurmountable barrier, but as a concrete engineering challenge. It's a gap the community now has the tools, like the scaling laws, to systematically work on closing over time. It gives us a real measurable target.
Can you give us a couple of those specific numbers again, just to make it concrete?
Sure. Looking at the results reported in their technical paper, Table 2. On ARCC, VaultGemma got about 26.5, while Gemma 3 got 38.3, and GPT-2 got 39.8. So definitely gap there. But then look at PIQA, common sense reasoning. VaultGemma scored 68.0. That's remarkably close to GPT-2's 70.5.
Wow, very close.
And on BullQ, factual questions, VaultGemma got 62.0, which was actually slightly better than GPT-2's 61.8 on that specific test in their evaluation.
Okay, so it really underscores that balance. It's a practical trade-off, a usable level of performance, bought for a massive gain in trust and safety.
Precisely. It shows you can have strong mathematical privacy and retain a very significant level of useful AI capability.
Okay, the benchmarks show the performance cost, the utility trade-off. But the ultimate justification, the whole point of paying that privacy tax, has to be the privacy itself, right? Did it actually work? Did VaultGemma truly succeed in preventing that dangerous memorization we talked about earlier? Or was it more of a theoretical guarantee with fingers crossed for the practical outcome? This feels like the real make-or-break test.
This is absolutely the litmus test. You're right. While the theoretical guarantees of DP-SGD are mathematically sound and give us strong reasons to believe it should work, empirical validation is absolutely key. We need to see the proof in practice, especially with a model this large and complex. Did it actually stop the memorization? To answer this definitively, the researchers conducted a very rigorous set of memorization tests specifically designed to push the model and see if any training data could be extracted.
Okay, how did they actually test for memorization? This is where it gets really interesting. Did the promise hold true in reality?
They used a straightforward but highly effective method. They took actual sequences directly from the model's massive training data set. For each sequence, they would feed the first half, say the first 50 tokens, into the model as a prompt.
Okay, give it the beginning of something it saw during training.
Exactly. And then they observed what the model generated next. The critical question was, would it generate the second half, the corresponding next 50 tokens, from that exact same training document? They tested for both exact memorization, generating the suffix perfectly verbatim, and also approximate memorization, which allows for some minor variations, but still clearly indicates that the model is recalling specific content from its training data. It was designed to catch any discernible trace of leakage.
And the results, the moment of truth.
The outcome was, frankly, stunning and definitive, and exactly what the theory predicted and what the researchers hoped for. While all the non-private versions of the Gemma models, when subjected to the exact same rigorous tests, showed detectable levels of both exact and approximate memorization. VaultGemma exhibited zero detectable memorization.
Zero across all their tests.
Zero detectable memorization, according to their published results. This empirical finding provides incredibly powerful, practical confirmation that the DP-SGD training process was fundamentally successful in achieving its primary goal, preventing the model from inadvertently regurgitating specific training data snippets. This result is the crucial payoff. It's what justifies the entire effort, the complexity, the computational cost, and that performance trade-off we call the privacy tax. The mathematical promise of differential privacy that the model shouldn't retain traceable information about individual training examples holds true in practice. For potential adopters in sensitive industries, for regulators, for anyone who needs demonstrable proof, this empirical zero memorization result is profoundly persuasive. It shows that the privacy tax isn't just an abstract penalty. It's a quantifiable price paid for a real, measurable, and highly effective defense against potentially catastrophic data leakage. It's a testament to the rigor of the engineering and the soundness of the DP approach.
Okay, so VaultGemma isn't just a cool piece of technology then. It feels like a really profound strategic move. One that could genuinely unlock AI's potential in entire industries, entire domains that were previously considered completely off limits because of those deep-seated privacy concerns. What kind of real-world doors does this actually open? What applications become feasible now?
If we connect this back to the bigger picture, you're absolutely right. Its primary, most transformative impact is precisely that, enabling the confident deployment of advanced AI in sectors where data privacy, confidentiality, and regulatory compliance are simply non-negotiable. Differential privacy's mathematical guarantees fundamentally change the risk equation for using LLMs on sensitive data. It shifts the conversation from, is this too risky, to, how can we leverage this securely?
So, like in healthcare.
Exactly. Consider healthcare and biomedicine. With VaultGemma, organizations can now potentially fine-tune models on private data sets, things like electronic health records, EHRs, doctor-sensitive clinical notes, maybe even genomic data. This opens the door for really innovative applications. Think about secure clinical document summarization to help overloaded doctors quickly grasp patient histories. Or AI assistants that can answer patient queries more efficiently, providing personalized yet private responses. Or even identifying patient cohorts for clinical trials based on aggregated, de-identified health patterns learned privately. And all of this could potentially be done without risking the exposure of protected health information. PHI, helping healthcare providers confidently meet stringent regulations like HIPAA in the US or GDPR in Europe. It could transform AI from a potential liability in healthcare into a truly trusted clinical assistant.
Okay, healthcare is huge. What about finance, another area with massive privacy needs?
Absolutely. The implications for the finance sector are equally profound. Financial institutions could now build secure AI assistants that operate on highly sensitive data. Customer communications, detailed transaction histories, confidential internal market analysis reports. This enables powerful capabilities like analyzing customer feedback sentiment at scale, automatically classifying complex financial documents for regulatory compliance, or even building more sophisticated fraud detection systems that learn from sensitive patterns without ever exposing individual customer data. All performed with a provable guarantee that individual customer data won't be compromised or memorized by the AI. That builds enormous consumer and regulatory trust.
And beyond healthcare and finance, what about general enterprise use or legal?
For broader enterprise and legal applications, imagine the power of securely building internal knowledge management systems. These AI systems could be trained on highly confidential internal documents, strategic plans, proprietary R&D notes, sensitive HR records, maybe even confidential source code or discovery materials for legal cases. Employees could then query this internal knowledge base, getting instant insights from the company's proprietary data without that pervasive nagging risk that the model might inadvertently regurgitate a trade secret, a sensitive client detail, or a piece of privileged legal information in response to someone else's unrelated query later on.
That alone sounds incredibly valuable for internal efficiency and security.
It really is. The implications for secure internal innovation, boosting productivity, and maintaining competitive advantage by safely leveraging internal knowledge are immense. VaultGemma potentially unlocks all of that.
Now, Google didn't just build VaultGemma. They released it with open weights on platforms like Hugging Face and Kaggle. That feels like more than just providing a tool. It seems like they're actively trying to cultivate an entire ecosystem around privacy-preserving AI. What does this open approach mean for the broader AI research community? How does it impact the future trajectory of developing privacy-first AI?
This move is profoundly significant, and it really represents a massive accelerator for the entire field. By releasing VaultGemma openly, Google establishes a much-needed public, reproducible baseline for privacy-first large language models. Before VaultGemma, research in this critical area was often quite fragmented. People were working on smaller, perhaps less capable models, where their work was done behind closed doors at large corporations, making it incredibly difficult for the wider community to effectively compare results, validate techniques, or build upon common foundations.
So everyone was kind of reinventing the wheel, maybe.
To some extent, yes, or working in silos. Now, researchers worldwide have a robust, large-scale, state-of-the-art implementation to work with. It provides a common ground, a shared starting point for innovation in private AI. This means researchers can now do several key things much more effectively. They can benchmark new techniques with unprecedented rigor. They can compare their own novel privacy-preserving algorithms or training methods directly against VaultGemma's established performance and privacy guarantees. That 110 baseline.
Apples to apples comparisons, finally.
Exactly. They could also build upon a solid foundation. Instead of starting from scratch, they can use VaultGemma's open weights as a starting point for further research, maybe developing more efficient private fine-tuning methods. We'll talk more about that. Or exploring entirely new model architectures specifically designed to work well under DP constraints, or even experimenting with combining DP with other privacy-enhancing technologies. And finally, they can validate findings at scale. Hypotheses about private AI that might have only been tested on small toy models can now be validated on a realistic billion-parameter scale model. This leads to much more robust, generalizable results that truly push the boundaries of what's possible in private AI.
So it really fosters collaboration and speeds things up.
Absolutely. This open approach fundamentally fosters global collaboration. It's explicitly designed to accelerate collective progress, turning the complex challenge of closing that privacy utility gap we discussed into a true community-wide effort, a shared scientific quest, rather than something only a few large labs can tackle.
When we talk about privacy, especially with powerful AI systems, the whole concept of trust is just absolutely paramount, isn't it? Why is open sourcing VaultGemma particularly strategic for building that trust? Wouldn't Google have potentially had a bigger market advantage by keeping this groundbreaking privacy tech proprietary? What's the deeper strategic play here with openness?
That's a really insightful question, and it gets to a core principle of building trust, especially in any domain related to security or privacy.
Yeah.
Transparency is key. Think about it. With a closed proprietary model, users, whether individuals or large enterprises, fundamentally have to take the provider at their word regarding its privacy features. They have to trust the claims made in the marketing material or the technical documentation.
Right, it's a black box. You trust the label.
Exactly. You trust the label. An open model, by contrast, deliberately invites scrutiny. It says, here are the weights, here's the research paper, here are the scaling laws, come look for yourself, kick the tires, try to break it. And paradoxically, that very openness to scrutiny is precisely what builds profound, lasting trust in the long run.
Because anyone can verify the claims.
Precisely. This transparency acts as an incredibly potent trust-building mechanism. By making the model's weights and the underlying research public, Google empowers the entire global community, independent security researchers, academics, developers at other companies, even motivated individuals to independently verify its claims about privacy. They can run their own tests, probe for vulnerabilities, deeply understand its behavior in a way that's simply impossible with a closed model. This open approach positions Google not just as an innovator in AI, but as a transparent leader in the responsible and ethical development of AI. And in today's climate, with growing public skepticism about AI, that leadership position built on transparency is incredibly valuable from a strategic perspective.
So it builds brand trust and potentially sets a standard.
Exactly. Furthermore, by providing the largest and most capable open model trained with strong differential privacy guarantees, along with the very scaling laws that guided its creation, Google is effectively setting a de facto standard in this nascent but rapidly growing field of private AI. Other models, other techniques will inevitably be measured against the VaultGemma baseline. This helps elevate the entire field, pushing everyone towards stronger, more verifiable privacy. It also helps democratize access to cutting-edge private AI technology, making it available beyond just a few tech giants.
And does it benefit Google more directly, too?
Potentially, yes. As industries like healthcare, finance, and government begin to adopt these kinds of privacy-preserving AI solutions perhaps built upon or inspired by VaultGemma, it may naturally drive demand for the specialized infrastructure needed to train, fine-tune, and deploy them. Infrastructure like Google's TPUs and the broader Google Cloud AI platform. So it creates this virtuous cycle. Openness builds trust, trust drives adoption, adoption fuels innovation, and potentially infrastructure demand, allowing Google to lead the conversation on AI privacy, shape industry standards, and build deep, trust-based relationships with enterprise customers who are desperately seeking genuinely secure AI solutions. It's a long-term strategic investment in the future of trustworthy AI.
VaultGemma is clearly a massive breakthrough, a really significant step forward. But like any cutting-edge technology, especially one navigating such complex trade-offs, it's also likely a powerful first step on what will be a much longer journey, right? What are its acknowledged limitations? What challenges still remain for privacy-preserving AI as a whole, even after this kind of leap?
That's absolutely right. And the development team behind VaultGemma has been commendably forthright and transparent about the current limitations. These aren't necessarily flaws in VaultGemma itself, but rather they reflect the inherent challenges of applying differential privacy at this scale with today's algorithms and hardware. They act as clear signposts, highlighting where the research community needs to focus its efforts next.
Okay, so what's the biggest limitation?
Unquestionably, the most significant limitation, the one we keep coming back to, is the utility gap. The privacy tax. As those benchmark results clearly demonstrated, there is still a noticeable gap in raw performance between VaultGemma and non-private models of a similar size built today. This means that for applications where absolute bleeding-edge performance is the only thing that matters, non-private models still hold an advantage. Closing this utility gap, achieving state-of-the-art performance while maintaining equally strong, rigorous privacy guarantees remains the central, most pressing challenge for the entire field. It's going to require further innovation in algorithms, model architectures, and maybe even hardware. It's the key balancing act.
Makes sense. What else?
Another limitation relates to its current context length and size. At around 1 billion parameters, and with that 1024 token context window, VaultGemma is exceptionally well-suited for many valuable, focused tasks, things like summarizing a single document, answering questions based on a specific piece of text, or maybe code completion within a file. However, it's currently less capable of handling really complex, long-form reasoning tasks, or tasks that require synthesizing information across many very large documents simultaneously. Many of the largest non-private LLMs are now excelling at those kinds of long context tasks, scaling up both the model size and the context window substantially, while still maintaining rigorous DP guarantees and manageable computational costs, is a significant engineering and research hurdle.
Right, scaling DP is hard. And you mentioned cost.
Yes. The third major challenge is the immense computational demands of DP training at this scale. As we discussed, the training process for VaultGemma is extremely resource-intensive. That need for massive batch sizes to counteract the DP noise requires very specialized hardware, like large clusters of Google's TPUs, and consequently, it demands significant computational budgets. This high cost currently limits the ability of many organizations, particularly smaller companies, academic labs, or organizations in resource-constrained environments, to pre-train these kinds of sophisticated, privacy-preserving models from scratch themselves. Making this powerful privacy technology more accessible and affordable to train is another key challenge for the community to address, democratizing the creation of private AI, not just its use.
But as you said earlier, these limitations aren't dead ends. They're really clear signposts pointing the way forward for future research. They tell us where the field needs to go next. So building on VaultGemma's foundational work, what's on the horizon for private AI? What are the exciting research directions for the road ahead?
Exactly. VaultGemma provides this incredibly strong foundation, a validated starting point, and a clear impetus for the research community to now systematically tackle these limitations and propel private AI even further. There are several key research directions that look particularly promising and could be incredibly impactful.
Okay, like what?
Firstly, and perhaps most obviously, scaling up to close the utility gap. The most direct path to improving raw performance is, simply put, to train even larger models. The new DP scaling laws we talked about provide a validated roadmap for doing this more efficiently and predictably than before. So, future work will undoubtedly focus on applying these principles to train private models with many billions or perhaps eventually even trillions of parameters. The expectation is that these much larger private models will significantly narrow or maybe even eventually close that utility gap compared to their non-private counterparts. Imagine having truly cutting-edge AI performance with provable privacy guarantees. That's a major goal.
Bigger private models. Makes sense. What else?
A second, incredibly important and practical area is developing better methods for parameter-efficient DP fine-tuning, or PEFT. We know pre-training a model like VaultGemma from scratch is super expensive. But fine-tuning an existing pre-trained model on a smaller, task-specific dataset is far more accessible for most organizations. So a key research direction is developing PFT techniques methods like LoRa, low-rank adaptation, or others that are compatible with differential privacy. If we can create efficient DP LoRa or similar methods, organizations could take a pre-trained private model like VaultGemma and adapt it to their specific needs, like analyzing their internal documents, using only a tiny fraction of the computational resources needed for full pre-training, all while maintaining a strict overall privacy budget.
That would massively lower the barrier to entry for customized private AI.
Absolutely. It would democratize the application of private AI dramatically.
Mm.
A third exciting direction involves creating hybrid privacy stacks. Differential privacy is incredibly powerful, but it's not the only privacy-enhancing technology PET out there. Each PT has different strengths and weaknesses. Future systems will likely become more sophisticated, employing hybrid stacks that intelligently combine the strengths of multiple approaches for even more robust and versatile privacy protection.
Hybrid stacks, like combining DP with other things.
Exactly. For example, you could imagine systems that combine federated learning, which allows models to be trained on data held in decentralized locations, like users' phones or local servers, without the raw data ever leaving those locations, providing strong data locality guarantees. You might combine that with DP applied during the local training or aggregation steps. Or maybe combine DP with secure multi-party computation, SMPC, which allows multiple parties, say different hospitals, to jointly compute a function on their combined sensitive data without revealing their individual inputs to each other. Or another powerful synergy, using a DP-trained model like VaultGemma for DP synthetic data generation. The private model learns the patterns in the real sensitive data and then generates an entirely artificial dataset that mimics the statistical properties of the real data but contains no actual real information. This synthetic dataset can then potentially be shared and analyzed more freely without direct privacy risks to the original individuals.
Wow, combining these different privacy techniques sounds very powerful.
It offers a lot of flexibility. And finally, a really significant theoretical and practical challenge, as we touched on earlier, is improving the privacy unit. Moving beyond the current sequence-level DP guarantee in VaultGemma to achieve true user-level DP would be a major leap forward. This would provide a stronger, often more intuitive guarantee, ensuring that the model's output doesn't reveal compromising information about the entirety of any single user's contributions to the dataset, no matter how many documents or interactions they contributed. Achieving robust user-level DP at the scale of modern LLMs, especially with complex real-world data where defining a user can be tricky, is a monumental but absolutely key frontier for the field to conquer. It would represent an even higher standard of privacy protection. #outro.
What an absolutely incredible deep dive into VaultGemma. It is just abundantly clear listening to all this that this isn't just another language model dropping another minor iteration. It feels like a profound statement about the future direction of AI itself. We've really seen how Google is tackling not just building powerful AI, but meticulously building trustworthy AI, right from the absolute bedrock, the foundation.
Precisely. VaultGemma truly is a landmark achievement, and it's landmark because it definitively proved that high-utility, genuinely useful language models can be built with these rigorous, mathematically backed privacy guarantees. It's not just theory anymore. It represents a genuine paradigm shift. It moved the whole conversation about AI privacy away from being just a theoretical ideal or some distant future goal, and makes it a practical, achievable engineering choice today. That privacy tax, as we've explored, is now a measurable cost, and those DP scaling laws provide a clear roadmap, a methodology for the entire community to work on systematically reducing that cost over time, making private AI ever more efficient and ever more capable.
And that decision to open source the model, the weights, and crucially, the underlying research in those scaling laws, They're not just leading the charge here, they're actively empowering and maybe even challenging the entire global AI community to build upon this groundbreaking work. It really feels like a call to action for collective progress in responsible AI.
Absolutely. You can see it as a real maturation of the field. The focus is clearly expanding beyond just chasing raw capability, beyond just making models bigger or faster. It's now fully embracing the crucial dimensions of responsibility, transparency, accountability, and ultimately user trust. This is a foundational step towards enabling broader, more confident AI adoption across every sensitive sector of our society and economy.
So, after unpacking all of this, the technical wizardry of DP-SGD, the strategic implications for industries, the ethical considerations around privacy and trust, what does this all mean for you, our listener? What's the one big thought, the key takeaway you hope our listeners chew on after this deep dive, something to really mull over as they watch AI continue its incredibly rapid evolution?
Hmm. The one provocative thought I'd leave everyone with is this. VaultGemma demonstrates powerfully that privacy doesn't have to be seen as a barrier to advanced AI. It doesn't have to be a limitation or an awkward afterthought bolted on at the end. Instead, privacy can be treated as a fundamental design principle, a principle that, when embraced from the start, actually enables the confident adoption of AI in the most critical, most sensitive, most impactful parts of our society. So the question to ponder is, what kind of world, what kind of applications that might have seemed unimaginable or too risky before become truly possible when you can finally mathematically trust an AI with your most sensitive information? What doors does that unlock?
That is a powerful question indeed, with truly profound implications for the future we're building with AI. Thank you so much for joining us on the deep dive and guiding us through VaultGemma. And thank you, our listeners, for tuning in. Until next time, keep pondering the possibilities and the critical importance of trustworthy AI.